Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp3 hybridization with one lone pair and 3 pi bonds in the main structure. And for this thing I'm taking an example of Xenon Trioxide, that's XeO3. So our today's example is Xenon Trioxide, that's XeO3. Here xenon is the noble gas, that is the inert element which will not form any compound. But the N. Bartlett at the University of British Columbia found that the ionization energy of xenon and the molecular oxygen is almost same. So he tried to make the compounds with that of xenon, and he was successful in making the compounds of xenon. So that's why we came to know about very much new compounds which were made by xenon. So xenon trioxide is one of them. So now let's talk about the xenon trioxide. Let's make its Lewis structure first. So I'm writing that's xenon, oxygen, oxygen, and the oxygen. Now let's talk about xenon. Xenon is a noble gas element. Xenon is a noble gas element. So obviously it will have 8 electrons in its outermost shell. So xenon is going to have 8 electrons in its outermost shell. So let's mark that 8 electrons around xenon. That's first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. Now let's talk about the oxygen. What's the atomic number of oxygen? It's 8. So its configuration will be 2, 6. That means oxygen is having 6 electrons in its outermost shell. So now let's mark the 6 electrons around all the oxygen atoms. So that's I'm taking the first oxygen. That's the first electron, the second, the third, the fourth, the fifth, and the sixth. Now let's talk about the second oxygen. First electron, second, third, fourth, fifth, and the sixth. Now let's talk about the third oxygen. First electron, second electron, third, fourth, fifth, and the sixth. Now all the oxygen atoms will make 2 bonds with xenon. So that's the first bond of first oxygen, and that's the second bond of first oxygen. Now that's the first bond of second oxygen, and that's the second bond of second oxygen. Now it's the first bond of third oxygen, and that's the second bond of third oxygen. Now let's count the number of valence electron around all the oxygen atoms after the formation of 2 bonds with xenon. Now I'm counting the number of electrons for the first oxygen. That is the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. That means the first oxygen has attained 8 electrons or the octet after the formation of 2 bonds with xenon atom. Now let's count the number of electrons around the second oxygen atom after the formation of 2 bonds. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So the second oxygen has also attained octet, that is 8 electrons after the formation of 2 bonds with the xenon atom. Now let's count the number of electrons around the third oxygen atom. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So that means third oxygen has also attained 8 electrons, that's octet, in its outermost shell after the formation of 2 bonds with the xenon atom. Now let's count the number of electrons around xenon after the formation of 2 bonds with 3 oxygen atoms. So that's the first electron, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, and the 14th. That means xenon has attained 14 electrons in its outermost shell after formation of 2 bonds with 3 oxygen atoms. Why xenon is capable of expanding its octet, that is having the 14 electrons in its outermost shell? Because xenon is having vacant orbitals in d subshell. That's why xenon is eligible for the expansion of the octet. Now let's talk about the hybridization of the xenon. So that's the xenon, and it's a noble gas. How do we come to know the electronic configuration of xenon? Let's talk about the group number 18. The group number 18 is helium, neon, argon, krypton, xenon, radon, and the oganesson. That's the period number 1, 2, 3, 4, and it's a fifth period. So configuration is 5s2, 5p6. So we got the configuration of xenon to be 5s2, 5p6, and a vacant d subshell, that's 5d0. Now let's make the orbital diagram in the form of the boxes. Sorry. So that's the 5s subshell, and we know that in s subshell we are having one orbital. Now in case of p subshell, here we are having the 5p. In case of p subshell, we have 3 degenerate orbitals, that is the orbitals with equal energies. So we got the 3 degenerate orbitals in 5p, and in case of 5d, we are having total of 5 degenerate orbitals in the d subshells. What are degenerate orbitals? The orbitals which have equal energies. Now let's fill the electron. The 5s is having 2 electron. The 5s is having 2 electrons, so let's fill them. In 5s, that's the first electron with a spin of plus 1 by 2, and that's the second electron with a spin of minus 1 by 2. And in 5p, we are having total of 6 electrons. So let's fill that 6 electrons according to the Hund's rule. And Hund's rule states that firstly, all the degenerate orbitals of 5p will get 1 electron each. After that, pairing will start. So that's the first electron, the second electron, the third electron. Now pairing will start. Fourth electron, fifth electron, and the sixth electron. Now let's come to the Lewis structure. In Lewis structure, what we can easily see? We can easily find out that xenon is forming total of 6 bonds. The xenon is forming total of 6 bonds, and I have already told you, whenever there is a formation of double bond, then out of that double bond, one bond will be sigma and the another will be the pi. So in case of first oxygen, the 2 bonds are formed, out of which the one bond will be sigma and the another will be the pi. So second oxygen also, the one bond is sigma, another is the pi. And in third oxygen also, the one bond is sigma and the another is the pi. So out of these 6 bonds, we are having 3 sigma bonds and 3 pi bonds. But firstly talk about total of 6 bonds. If xenon has to form total of 6 bonds, that means in case of orbital diagram, we must have 6 electrons in different 6 atomic orbitals. That means we can say that 6 atomic orbital must have one electron each, so that xenon will be able to form the 6 covalent bonds with the oxygen atoms. For that thing, what we have to do? Here, firstly, this is the ground state. Firstly, this is the ground state of the xenon. If xenon has to form these 6 covalent bonds, then in case of xenon, we must have 6 atomic orbitals containing one electron each. Only then that 6 orbitals will overlap with the atomic orbitals of oxygen containing one electron for the formation of the covalent bond. So here we are going to excite 3 electrons to the further orbitals. So That's the first electron which will jump or excite in the d orbital. So that's the second electron which will excite from 5p to the 5d, and that's the third electron which will excite from 5p to the 5d. So let's make the excited state. That's the 5s orbital. These three are 5p orbitals, and these 5 are 5d orbitals. So what we got? We got the 2 electrons in 5s, 1 electron each in 5p orbital, and 3 electrons in 3 orbitals of 5d. So here we can see that we got the 6 orbitals containing 1 electron each, which makes xenon eligible for the formation of 6 covalent bonds by the overlapping of atomic orbitals of the oxygen atom. So I'm repeating it again. In case of xenon, we got the 6 atomic orbitals containing 1 electron each. So now xenon is eligible for the overlapping of these 6 atomic orbitals with the atomic orbitals of the oxygen atom containing 1 electron each. So for the formation of 6 covalent bonds. Now let's come back to again Lewis structure. How many sigma bonds are there? Here are total of 3 sigma bonds. Here we are having total of 3 sigma bonds, and I have already told you in the previous lectures also that hybrid orbitals will form only sigma bonds. So that means during the hybridization process we have to consider the only 3 atomic orbitals of xenon containing 1 electron each, because hybrid orbitals forms only sigma bonds, and in case of XeO3 we are having total of 3 sigma bonds. That's why for the hybridization we will consider only 3 atomic orbitals of xenon containing 1 electron each. So first of all, this was the excited state, and in the hybridization process we have to consider the atomic orbitals of fifth shell containing the electrons. So I'm considering one of the s orbital and 3 p orbitals containing 1 electron each. So by this way we got the 3 atomic orbitals containing 1 electron each for the formation of 3 sigma bonds. The pi bonds are not considered in the hybridization, or we can say that hybrid orbitals does not form the pi bonds. So here 1 s orbital and 3 p orbitals will intermix. In the previous lectures I have already told you, in the hybridization process the s orbitals are always involved. So in this case s orbital is having 2 electrons, and that will be considered as the lone pair in case of hybrid orbital. So let's understand that. Firstly, we have intermixed 1s and 3p orbitals. This intermixing is called hybridization. This intermixing is called hybridization. Here the 1s and 3p, total of 4 atomic orbitals have mixed, so we will get 4 new hybrid orbitals. 4 new hybrid come degenerate orbitals. That means all the new 4 hybrid orbitals will have equal energies. So we got the 4 new hybrid orbitals because we have mixed total of 4 atomic orbitals, that's 1s and the 3p. So we got the 4 new hybrid orbitals. Now what will be the name of these 4 hybrid orbitals. So in the intermixing process, we have mixed 1s and 3p. So we got the hybridization to be sp3 and the name of hybrid orbital to be the sp3. So first hybrid orbital is the sp3. Second hybrid orbital is again sp3 hybrid orbital. The third one is also sp3 hybrid orbital, and fourth one is also sp3 hybrid orbitals. So in case of sp3 hybrid orbitals, we are having 25% s character and 75% p character per hybrid orbital. So we got total of 4 hybrid orbitals whose name is sp3 each. Now, how many electrons we have to fill now? During the intermixing, we were having 2 electrons in 5s and 3 electrons in 5p. So total we have to fill 5 electrons in the hybrid orbitals according to the Hund's rule. So that's the first electron, second electron, third electron, fourth electron, and the fifth electron. After that, what we have left with? We have left with 5d shell. Let me make that also. So that's our 5d, and in 5d we are having total of 3 electrons. Let's fill them also. So that's the first electron, the second electron, and the third electron. Now whenever any hybrid orbital is having total of 2 electrons, so in the first sp3 hybrid orbital we are having 2 electrons, that will be considered as the lone pair of electrons. Let's come to the Lewis structure. Here we are having this to be the lone pair of the electron. This is the lone pair which we have got in the hybrid orbitals. Now let's talk about the oxygen over here. I'm talking about now oxygen. What's the atomic number of oxygen? That's 8. So what will be the configuration? That will be 2s2 2p4. Let's make the orbital diagram of 2p. In 2p we are having the 3 degenerate orbitals. Now here in 2p we are having total of 4 electrons. Let's fill them according to the Hund's rule. That's the first electron, second electron, third electron, and the fourth electron. So that's the 2p orbital diagram of the oxygen. Now let's use it in hybridization. So I'm talking about the first oxygen atom first. I'm drawing the 2p of the first oxygen. That's the 2p of first oxygen. In 2p we are having total of 4 electrons. Let's fill them, the first, second, third, and the fourth. Now what next? Here we are having in 2p the 2 atomic orbitals which are having 1 electron each. Now the first orbital containing 1 electron of oxygen will have an head-on overlap with the sp3 hybrid orbital of xenon to form the sigma bond. So we got the sigma bond of type sigma sp3p, because this sigma bond has been formed by head-on overlap of sp3 hybrid orbital of xenon with the p orbital of the first oxygen. That's why it is named as sigma sp3p. Now let's talk about the another atomic orbital which is having 1 electron. Now the other atomic orbital of oxygen which is having 1 electron will have the sidewise or the lateral overlap with the 5d orbital of xenon for the formation of the pi bond, and this pi bond will be named as p pi d pi bond. Why so? Because this pi bond has been formed by sidewise or lateral overlap of p orbital of first oxygen with the d orbital of the xenon. Now let's talk about the second oxygen. Again, that's the 2p4 of second oxygen. Here also we are having 4 electrons, 1, 2, 3, 4, and here we are left with 2 atomic orbitals of 2p, which is having 1 electron each, which will going to form the bonds with the xenon. And here the first orbital containing 1 electron in case of 2p of second oxygen will have head-on overlap with the sp3 hybrid orbital of the xenon to form this sigma bond. So we got the another sigma bond, that's sigma sp3p, because this sigma bond has been formed by head-on overlap of sp3 hybrid orbital of xenon with the p orbital of the oxygen. Now we are left with the another atomic orbital of 2p of second oxygen, which is having 1 electron, which will have the sidewise or lateral overlap with the 5d orbital of xenon for the formation of pi bond. So here we again got the pi bond to be named as p pi d pi bond, because this pi bond has been formed by the sidewise or lateral overlap of p orbital of oxygen with the d orbital of the xenon. Now finally let's talk about the third oxygen. That's the 2p of the third oxygen. That's the 2p4 of third oxygen. Here again 2p is having 4 electrons. That's first, second, third, and the fourth, and here again we have left with 2 atomic orbitals of 2p, which is having 1 electron, which will form the pi bond, sorry, sigma and the pi bonds with the xenon. So the first 2p having 1 electron will have head-on overlap with the sp3 hybrid orbital of xenon for the formation of the sigma bond. So we got the third sigma bond, which is named as sigma sp3p, because this sigma bond has been formed by head-on overlap of sp3 hybrid orbital of xenon with the p orbital of the third oxygen. And here we have left with again 1 orbital containing 1 electron, which will have the sidewise or lateral overlap with the 5d orbital for the formation of pi bond. So we got the third pi bond, which is named as p pi d pi bond, because this pi bond has been formed by sidewise or lateral overlap of p orbital of oxygen with the d orbital of the xenon. So here you can easily see that hybrid orbitals are forming sigma bond with the 3 oxygen atom, and the 5d orbitals are forming pi bonds with the orbitals of the 3 oxygens. So I'm clearing it again that hybrid orbitals are forming only and only sigma bonds, and the unhybrid orbitals of 5d of xenon are forming the pi bonds. Now let's talk about the structure. Which hybridization it came to be? That's sp3. What's the standard structure of sp3? That's tetrahedral. The central atom is xenon over here, and in xenon we are having firstly 1 lone pair, the orange color. I have marked the lone pair with the orange color, you can see that. So that 1 lone pair I am taking on one of the position of the tetrahedral geometry. Now we are having 3 oxygen atoms who are forming 2 bonds with the xenon. So that's the first oxygen, that's the second oxygen, and that's the third oxygen. Here we are having 3 sigma bonds, and that sigma bonds are sigma sp3p, here also sigma sp3p, and that's also sigma sp3p, because this sigma bond has been formed by head-on overlap of sp3 hybrid orbital of xenon with the p orbital of the oxygen. And we are having 3 pi bonds. The first pi bond will be named as p pi d pi, the second also it's p pi d pi, and third one also it's p pi d pi. Let me write it over here. Third also is p pi d pi, because these pi bonds has been formed by sidewise or lateral overlap of p orbital of oxygen with the d orbital of the xenon. Now, as here also the lone pair is involved, so this geometry will not be called as tetrahedral. This will be called as trigonal pyramidal. That's also trigonal pyramidal. Now, let's come back to the hybridization. Let's talk about the energy points. Here, in this case, we are having two endothermic processes. Firstly, here's the consumption of electron during the promotion of the electron. So that's called promotional energy. So I'm writing here's the consumption of promotional energy. Now after that, there's the intermixing of the there's the intermixing of the atomic orbitals of xenon to form the hybrid orbitals. So here also the consumption of energy called hybridization energy. Here also the consumption of hybridization energy. Now, as we are having two endothermic processes, so here we are having the formation of new 6 bonds, out of which the 3 are sigma and 3 are pi. So the energy will be released. So I am writing during the formation of 3 new sigma bonds and 3 new pi bonds, comma, energy is released, which will compensate promotional energy and hybridization energy. That's why the formation of xenon trioxide is practically feasible or possible. So that's all about the xenon trioxide. Hopefully you got the hybridization, that's sp3 hybridization, out of which one sp3 hybrid orbital is having one lone pair and the other 3 sp3 hybrid orbitals are forming sigma bonds with the 3 oxygen atoms, and the unhybridized orbitals of 5d are forming pi bonds with the 3 oxygen atoms. So that's all for today. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.